Hello everybody, I welcome you to dealing with proposition 11 of Gottfried Wilhelm Leibniz's work on the arithmetic quadrature of the circle, parabola and hyperbola. And in proposition 12, or 11 rather, Leibniz is showing that you can cut away from the semicircular figure, which is this one. You can cut away a sector or an area in infinitely many ways, in a way that you can produce an analog figure based on the principle of creating the resecting figure, of which you know that it will always have the double of the area of the which you cut away from the semicircular area. And more important even is to say in this proposition that this also counts, or this relationship is also true when you make this area which you cut away infinitely small. And we're going to go through a succession of steps in order to elaborate on this very statement. So first of all, you have the semicircular curve, just the very same way as we dealt with in the previous propositions. You have the axis, you have the conjugate axis, and additionally we placed on the very lower apex point of the semicircle a point which we call micron. And this micron point has a tangent which extends to the right here and is actually parallel to the conjugate axis because it's the tangent of the very apex point. And this tangent, and especially the point micron, are going to play a role later on. First of all, now let's draw out the resecting curve and the principle of how the resecting curve is coming about. We dealt with in proposition 6, 7, and 8, and we're not gonna go into the details about this. So if you want to know how a resecting curve is created, I advise you to watch proposition 6, 7 and 8. And the resecting curve basically designates an area which is called the resecting figure, which is bound by the very resecting curve, which extends to the infinite, and is also bound by the basically the tangent of this very micron point, which we talked about before, and the axis. And this area is called the resecting figure. And in propositions 7 and also 8, we already established that when you place a point on the semicircular curve and you create a segment like this, and you draw out a part of the resecting figure which is called the segment figure, which is shown in green here, that these areas relate to each other such that the segment is always half the size of the segment figure. And this is what we already know from the previous propositions. So, and in the next step in the proposition, Leibniz was putting out some wording in where he said that you could cut basically away an area very much like the blue part of the semicircular curve and produce a figure which is double the size of this very cutaway area. And if you read the words not carefully enough, then you very much come to the or get the impression that he meant actually that the blue area of the semicircle here is actually half the size of the very lower part here of the resecting figure, which we've drawn out in red. And only by reading a bit more carefully in the proposition 11 and also relating to the knowledge of the previous propositions, you know that this cannot actually be true. Because if you think about it, you have the entirety of the resecting figure and it's sort of divided now by the ordinate and creates an upper part of the resecting figure, which is the same as what we call the segment figure, and the lower part of the resecting figure. And since we know that the segment figure is the double of the segment, there must be the difference, what is left when you create the difference between the entire semicircle and the segment. So when you take the segment away from the entire semicircle, that this must actually be constituting the half of the area which is bound by the very ordinate we've drawn, the axis, then the tangent of the micron point, and the lower part of the resecting curve, namely this red area here. And hence it is the case that the areas relate to each other like this, actually, that it is actually the very blue sector here, which we've drawn out now, that this actually is the correct area, which is exactly half the size of this part of the lower part of the resecting figure. And this is important to keep in mind and to point out, because proposition 11, if you read it, you can very quickly come to the wrong conclusions. And we're going to elaborate further now. He said that you can cut in infinitely many ways a part away from the semicircle and always create a figure which is always double the size of the very cutaway part from the semicircle. And this is certainly so far true for this sector. So you can create infinitely many of these sectors, but it's always the same type of sectors. Yeah, and hence he thought about not only sort of moving this point around the semicircular curve, but he thought of what would happen when you actually move the conjugate axis itself relative to the semicircle. And this is what we're going to try to show now in the next step. So what happens to the very resecting figure or resecting curve, first of all, when we place the conjugate axis somewhere else? So hence I'm now using this little handle here and constitute this ordinate now actually as the conjugate axis. And we are applying the very same principle as usually, using the tangents, and where the tangents intersect the conjugate axis, you drop verticals, and where these verticals intersect the ordinates of these points, then you know that this point must belong to the resecting figure. And then we trace these points and draw the resecting figure out. So when we do this, you actually see that the resecting curve looks a lot different when you place the conjugate axis somewhere else, especially if you not place it on one of the apex points. So as soon as you move it away from the apex point, you can consider the resecting figure basically as two parts, an upper part and a lower part, and both parts converge or extend to the very infinite in length to the right here, and the lower part as well. And as soon as I reach one of the apex points again, then we just have our usual resecting figure, the same type which we were dealing with before. And this is an important step to take, because first of all he defined, so if you place the conjugate axis at the very center of the semicircle, you get a figure which Leibniz later on calls the angle figure. And the angle figure will have a very interesting relationship to the hyperbola if we get later to proposition 13, and where we will see this relationship playing out. But for now, displacing the conjugate axis actually will help in defining areas which you can cut away from the semicircle and to create different types of sectors by still knowing that the relating part of the resecting figure is still double the size of the very part which you just cut away from the semicircle. So let's look at the blue part, for instance. And the blue part, according to the construction principle and the propositions we dealt with before, especially proposition 1 and proposition 6 through 8, we know that the very blue part of the semicircle, which we just cut away, so to speak, will be exactly the half of this lower part of the resecting figure. And hence it must be the case that the upper part of the semicircle, which is uncolored here, is the very half of the upper part of the resecting figure, which is basically not filled with red right now. So this is all we know, because we know the principles we've established in proposition 1 and proposition 6 through 8. And then we can take another step. We could be interested in knowing what happens when I, so to speak, remove the very C2 point here, when I move it away from the conjugate axis. What is going to happen then to my area? So what happens is basically that you create another sector which is above the conjugate axis, and it creates, by using the ordinates and the boundary of the upper resecting figure or resecting curve and the bound of the conjugate axis itself and the axis, this very red area here will be known to be exactly the double of this upper sector. And all just by means of the principle, and all by knowing the principle, which we develop by the use of creative human mind. And actually Leibniz's creative mind. But any mind can be as creative as his. So, and now we actually have what we wanted in infinitely many ways. You could cut away from the semicircle infinitely many types of different sectors. And these sectors, they may be even infinitely small, because if you have, for instance, moved this C point to the very close to the apex point of the as the micron point here, I still will know, even though the resecting figure extends to the infinity in length to the right here, that this principle will still hold, that the relationship will still hold. And hence it is not so miraculous anymore that the area underneath an area which extends into infinity in length, this area is actually finite, because if you consider this relationship and you know that the area sector here is certainly finite, which you can actually conceive already visually, then you can draw the relationship also to an area which extends infinitely to some side. And the way this was dealt was initially somewhat problematic, because the area of the lower part here of the resecting curve is basically bound by the ordinate of the micron point as the apex point of the semicircle. And this is actually then, in terms of this resecting curve, an asymptote. And because it's an asymptote, because the resecting curve converges toward it, but without ever reaching it. And this causes a paradox, because how can it then be that if this resecting curve never reaches the asymptote, how can this area then be finite? And this is first of all clarified by the relationship, which we've drawn out between these sectorial triangles, these infinitely small sectorial triangles of which the sector is composed, and the corresponding elementary rectangles of which the resecting figure is composed. And Leibniz goes into an elaborate dealings on the infinitesimal, because he said that he actually never found someone who could or who was able to square or quadrate an area between a converging curve and an asymptote, because of the fact that those two never will meet. So because you have basically the asymptote as an infinite line, and hence he was introducing a point which he called here micron in brackets. And he said that this point micron in brackets is located in basically infinitely small distance above the micron point on the curve, on the semicircular curve. And this takes care of the fact that you do not deal with an asymptote anymore, because it's although the distance between micron and micron brackets is infinitely small, micron brackets is still a different point than micron, so it's different from the apex point. But if you create the ordinate from this point, it's still to be considered as an infinitely long line. So we have now an infinitely long line, but which is not an asymptote. And this caused the whole concept playing out of considering such a line as infinitely long, but bound. This line is bound, he said. And this concept bears now these two qualities, that you don't deal with an asymptote anymore, which is infinitely long, but you can basically consider this line, due to the character of infinity of this curve, as because the distance between those two is infinitely small, the ordinate it creates can still be considered infinitely long, but being bound. And he explains this by saying that if you, for instance, consider the rectangle between, or which is bound by the very infinitely small distance between the micron point and the micron bracket point, and toward the very point lambda here, which we could imagine to be somewhere in infinity, then you would actually have a rectangle which is composed, or which would be the product of an infinitely small quantity and an infinitely large quantity, being the length of this ordinate of the micron bracket point. And this is the whole trick, because Leibniz said when you multiply sort of an infinitely small quantity with an infinitely large quantity, you actually get a finite value. And this is not exactly being proven, and he already also says this in proposition 11, but the concept actually is enough to be convincing, especially when you relate the principle between the sector and this area to the whole category, because you know by principle that the sector is half the size of the area of the resecting figure, because both are composed of infinitely small areas, which are triangles in case of the sector and rectangles in case of the resecting figure. And those two are related such that the sectorial triangles are always half the size of the sectorial elementary rectangles. And if you sum them all up to become those areas, this relationship still must stand also for the sums. And Leibniz wrote out an interesting scholium for this, which we shall deal with in a bit. And this type of a problem of a curve extending or converging toward an asymptote into the very infinite was also dealt with before by a guy named Evangelista Torricelli, who actually dealt with a rotational body of the hyperbola. Imagine you draw out the hyperbola and you start from x equal 1, and then you rotate this hyperbola around the x-axis. You get a type of a trumpet shape, and because of this shape, this rotational figure was also termed like Torricelli's trumpet or Gabriel's horn or these kind of things. And Torricelli was able, by means of the Cavalieri principle, to show that the area of this, or the surface area of this very trumpet, is infinite, while the volume of this trumpet is actually finite. And this at the time was a big paradox. But when you think about it, the paradox actually gets resolved by the very principle that when you create an area on the hyperbola by placing a point on the hyperbola and creating the rectangle, being made up of the abscissa and the ordinate of this point, and the very axis of the what nowadays would be called a coordinate system. And this rectangle you make up this way has actually exactly the same value, no matter where you place the point on the hyperbola. And hence it must be also, when you place this point infinitely an infinite distance away along the x-axis on the hyperbola, then you still know, even though you can visually sense it anymore, that this area is still the same, because nothing changes about the principle of the hyperbola, also in infinity. And this fact actually helped Torricelli to resolve this. And Leibniz is doing a very similar thing here. It's just not that he uses the hyperbola, but he knows that the resecting figure is convergent toward this very asymptote down here. And instead of using this rectangle principle of the hyperbola, he's just using the principle of the semicircle, and basically referring this area, which seems to be infinite because it extends in length to infinity, referring it by principle to a finite area of another kind of figure. And here with Leibniz it was the sector, and with Torricelli it was the rectangle made up by an abscissa and an ordinate of a point placed on the hyperbola. And if you think of it this way, then it appears not so mystical and paradoxical anymore, because you consider that principles always stay the same. And now we're gonna sort of go through some steps again in terms of the micron point and the micron bracket point. So to bear in mind that the micron bracket point is basically an infinitely small distance away from the micron point, hence they're not the same. And hence the ordinate, which is made up by the micron bracket point and the very point lambda, which would be extended here into the infinite, would not constitute an asymptote. So that's what we draw out here. Line micron lambda is not an asymptote, but it's still an ordinate of point micron, being an infinitely small interval, micron brackets, above the asymptote. And hence it is called that the line micron bracket lambda, which we must imagine infinite distance away from the axis, is infinitely long, but it is not unbound, because by placing the micron bracket point above the micron point in an infinitely small distance, we eliminate the nature of the asymptote for this very ordinate of the micron bracket point. And hence this enables us to actually constitute that the area which extends here into the very right is finite. And because we can say this, because the relationship holds to the sector, which we have proven always to be the half of the very segment figure, and hence also in the infinite of the whole resecting figure, or rather the infinitely long part here of the resecting figure. And we established this principle in proposition 7. Okay, so now we're going to read out an interesting scholium, which probably also gives some insights at what Leibniz meant by when he said, or when he talked about the line being infinitely long but not unbound or unbound, and what this means. That's why we're going to read out a little scholium which he wrote now for proposition 11, and this is going to be very interesting. So I'm going to read it out for you. Scholium proposition 11. Worthwhile mentioning is a consideration of areas which extend into the infinite in their length, but still are finite in size, area. As far as I, so Leibniz, am concerned, the old wise men did not conceive of such a thing, and it seemed astonishing enough to them that there are certain asymptotic straight lines which more and more close in on a curve, but will actually never reach it. As the first one, as far as I know, Torricelli did measure the infinitely sharp hyperbolic body, and transformed it into a certain finite solenoid. Father Grégoire de Saint-Vincent has quadrated an infinite area which is bound by two hyperbolas in a certain way, and the deservedly famous Christian Huygens was transforming the infinite area of a cissoid back to a circle. Also, the outstanding geometer John Wallis demonstrated how countless the hyperbolids are, the areas of which can be found, even though they are infinite in length, and furthermore how those areas which do not allow for this can be distinguished by a probabilistic method, because it involves the highest degree of sharp-mindedness, although it makes use of induction. It's a very nice little formulation here, full of irony. Sharp-mindedness, although it makes use of induction. Alright, adding the content of proposition 22, to which we will get later, where we proved it, accounts for this. Proposition 7 has provided us with a way to prove the existence of infinitely many kinds of figures being infinitely long, which are equal to the double of an arbitrarily small segment or sector of any provided curve. That this also can be done using other methods, we do well know. Apart from this, our honesty does not tolerate the concealment of the fact that those things are not as astonishing as they appear to people at the first look. The Honorable Father Pardis of the Society of Jesus, well known to the academics by his elegant writings and worthy of a longer life, attributed such big weight to these kind of thoughts that he believed to deliver a sufficiently effective argument to prove the immateriality of the soul, as he asserted in the preface of the Geometric Compendium. It seems to me that through itself the nature of the mind and the operations, the more so as those through which it will redirect to itself, are enough to distinguish it from body or from the thing which is equipped only with twofold, namely the extension and the mass. Yet I would not like to deny that certain special operations at least appear more adorable than the rest, such that even though they are not suitable to be used for proof, they are at least suitable for convincing. But concerning this activity of the mind, with which we measure infinite areas, it does not contain anything unusual because it rests on a certain fiction, and on the condition of a certain, though limited, but infinite line, does proceed without any effort, as if we would measure an area which is finite in its length. I would be very amazed if someone could transform a completely unbound area itself, which is located between a curve and a complete asymptote, to a finite area. Such an operation has not come to my knowledge, and I believe it neither has come to the knowledge of others. Adding the corollary of proposition 14 will account for this. But since this talk about lines which are infinite but not unbound will appear paradoxical to some, it must be remembered that the difference between the infinite and the unbound is as big as the throughout big difference between the indivisible and the infinitely small. Deceiving is the geometry of the indivisibles if it is not explained with regards to the infinitely small, for the truly indivisible points are not used without danger, but one must use lines, though infinitely small, but still lines, and therefore divisible ones. In absolutely the same fashion, an unbound quantity differs from an infinite one, for the magnitude of an unbound line is in no way subject to the geometric considerations more than those of a point, namely, how points even of infinite count are added and subtracted to and from a limited line in vain. So can a limited line neither produce nor exhaust an infinite one, no matter how many times it was repeated. This is different with a bound but infinite line, which is thought to be produced by some amount of finite lines, even though this amount exceeds any number. And how a limited infinite line is composed of finite ones, so a finite line will be composed of infinitely small but yet divisible lines. Hence it cannot be said that a limited line is the proportional one between a point or a smallest line and an unbound or largest one, but it can be said that a finite line is the averaging proportional not only certainly, but in reality and accurately, between a certain infinitely small and a certain infinite. And it is true that a rectangle made of an infinite side and an infinitely small one can be equal to a certain finite square. And that is indeed true with the cone section hyperbola. If, for instance, the curve d for sigma lambda was a hyperbolic one, the center of which was micron, and from which micron to micron brackets be some infinitely small abscissa, the ordinate micron lambda would be infinitely long, namely longer than any arbitrarily givable one, and the infinite rectangle micron brackets lambda, which is bound under the infinite and the infinitely small line, and it would be equal to a certain finite fixed square due to the hyperbola nature. Unbound I therefore call that which at least on one side cannot be determined a last point, but something infinite I call a quantity, be it bound or unbound, if we only think of it being greater than an arbitrarily or by numbers allocable one. To investigate if the nature of these things can bear these kind of quantities is a matter of the metaphysician. For the geometer, it is enough to prove what follows from the assumptions themselves. So I hope this clarifies a little bit the concept of the infinite and the infinitely long and bound and unbound. And I hope you enjoyed this information a little. And if you have trouble of conceiving this very difference between the infinite and the infinite and unbound, and the infinite and bound and so far, I recommend watching this video again, and especially the passage of the scholium of proposition 11. And it is thought-provoking, but it represents the very basis which allowed for the development of the concept of the infinitesimal calculus. And thereby I will conclude proposition 11 now, and hope you stay tuned and continue watching the other propositions as well. Thank you very much, and bye-bye.